This is Algebra 2 with trig, Unit 4.2. We're going to find the equation of an inverse function. So just a reminder that a function is a relation in which each input, which is the x value, there is only one output, which is a y value. So for every x that you plug in, you can only get one y for that given x value. So if we look down here, we see that every x is different. Therefore, it doesn't really matter about the y's. It's okay if a y repeats. For example, here, -2, -1, -1, 1, 0, 3, 1, 5, 2, 7. That's a linear equation. Its inverse, -1, -2, 1, -1, 3, 0, 5, 1, 7, 2. Its inverse is also a function. Okay, so this is going to be a function. If we look at this one though, -2, 8, -1, -1, 0, -4, 1, -1, 2, 8. Here we have a parabola. And when we reflect that across the line, y equals x, we're going to get these points, which is 8, -2, -1, -1, which is always right on the line of reflection, -4, 0, -1, 1, 8, 2. You'll see that a vertical line test crosses that graph twice. So we're just going to call this a relation. A function is a relation, but a function is a special relation saying that every x value only has one y value. I think about it as the cost of a milkshake has one price to it. Yes, there could be different sizes, I know, but the cost of a donut has one price to it. So it would be weird if there were different prices for the same donut. This would indicate different prices for the same donut, same number of donuts, two different costs. So that's not a function. We're just going to call it a relation. We look down here at what these would be: -2, -6, -1, 1, 0, 2, 1, 3, 2, 10. And that's much more like a linear equation. You'll notice that up here, the repeated y values turned into repeated x values that gave you different y values. So you can tell just by looking at the table if it's going to be a function or not. If the same x value gives you two different y values, then it's just going to be considered a relation. Well, where here, all the y values are different. So when you switch it over, they're going to become x's that are all different. Your x's are all different. So when they switch over, there's no repeats. This is going to be a function. If we reflect this over the line, we're going to get something that looks similar to this. And you see that that's going to pass the horizontal or the vertical, sorry, vertical line test. What we notice is the inverse of a function is sometimes, or even often, is sometimes a function too. You can look at a given table of values and decide, or how can you look at a given table of values and decide if its inverse is a function? If the y values repeat numbers, if the y value repeats, then the inverse will not be a function. Here we had y values that repeated. So when we looked at the inverse, we saw that the y's become the x's. So they're repeated, and they give us two different types of y's. Recall that the vertical line test is a test we can do on a graph to determine if it's a function. We've talked about that some here. A vertical line indicates that the x value that this is representing only has one answer for that graph. So it's going to cross that graph at one spot, which indicates it is a function. How could we look at a graph and decide if its inverse is a function? When we looked at this graph, is there a way to notice that its inverse is not going to be a function, that the vertical line is going to cross twice to the inverse? What can we look at for a original graph to determine if its inverse is going to be a function?
A horizontal line?
Yes. Look to see if any y values repeat in the original graph. So, like you said, this is going to be called the horizontal line test. The inverse of a function f is also a function if and only if any horizontal line intersects the graph only once. So if we look across here and we consider the original graph, you run a horizontal line through that, it's going to cross only one time. So that means a vertical line is going to cross its inverse only one time. Whereas here we looked at the parabola, a horizontal line is going to cross the parabola twice. It has repeated y value. So its inverse is not going to be a function. The original one might be a function. Horizontal line test does not test for a function. It tests if the inverse is a function. This is a test we can do on the original function to decide if the inverse is a function too. So here's our x cubed graph. We do a horizontal line test to it, horizontal line test. It crosses at exactly 1 point. So the inverse is a function. Its inverse would look something like this. And a vertical line test would cross once. So it is a function because the horizontal line test crossed once. The vertical line test of the inverse is going to cross once. Here's our horizontal line test. It crosses the graph at 2 spots. That means when we reflect it over the line y equals x, it's going to have a vertical line that crosses it twice. A horizontal line looks into the future. It looks into the future, it looks at the inverse and determines if it's a function. If it crosses twice, the inverse is not a function. All right, so now we're going to determine if these equations have an inverse that is a function. You might have an idea just by looking at the equation, but let's look at the graph. 1, 2, 3, because you start at the y-intercept and you do the slope of -2, which is down 2 over 1 and up 2 over 1. So that gives us our graph. There's f of x, -2x minus 3. We'll do a horizontal line test. Horizontal line test. And you see that it only crosses once. So is the inverse a function? I don't know. I can't even see the inverse. Oh, if the horizontal line test is going to cross this once, then it's going to cross the inverse only once for the vertical. All right. So we're going to say, is the inverse a function? The answer is yes. Because the horizontal line test, I'm sorry, the original, let's say that, the original graph passes the horizontal line test. Because it only crossed it once, that horizontal line passes the test. So yes, the inverse is a function. This is an absolute value graph. where your H value is 1 and your K value is 2. So you're over 1 and up 2 with a slope of 3. And we do a horizontal line test to it. This equation, by the way, is f of x equals 3, absolute value of x minus 1 plus 2. The horizontal line test crosses in 2 spots. So that means it's inverse. It's a vertical line is going to cross the inverse in 2 spots. It'll kind of look like this, but it's actually going to be above the x-axis, not below the x-axis. It's pretty much exactly going to look like that, but that's hard to see. So anyway, it's reflecting over the line y equals x, and it would be over here. So we get no, the inverse is not a function. Because the original graph fails the horizontal line test. Here we're looking for x cubed. This is x cubed plus 1. Well, we know the x cubed parent function, 0 times 0 times 0. This is for y equals x cubed. If you were to plug in -2, -2 times -2 times -2 is -8. -1 times -1 times -1 is -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So you know that those are the points of x cubed. Now we need to increase all of those points by 1. There it is. That is f of x equals x cubed plus 1. And a horizontal line test is going to cross it at exactly 1 spot. So yes, because the original graph passes the horizontal line test. Now we're going to talk about restricting the domain, looking at only certain parts of the graph, not the entire graph. If we look here and try to graph this out, we know we're going to have a parabola, which is a U shape. It's going to have a vertical stretch, and it's going to be translated down 1. So if we translate down 1 now, and we think about the parent function, which is up 1 over 1 up 1 over 2 up 4 over 3 up 9 all right, I do those dots real light because we don't want those dots. That's the parent function. That's x squared. We want to be able to have 2 times x squared. So we're going to go up twice that amount. And then twice that amount. So that is f of x equals 2x squared minus 1. And we can tell that a horizontal line test is going to cross it in 2 spots. Is the inverse a function? No. The original graph fails the horizontal line test. Okay. Well, what if we do this funny domain thing? What if we only look at values that are greater than or equal to 0? What if we only look at that part of the graph? We're not going to look at the other half of the graph. We're only going to look where x values are greater than or equal to 0. We're not going to look at the x values less than 0. So now we do a horizontal line test to it. And we see that it crosses exactly once. So if you restrict the domain, it is possible that, yes, the inverse is a function. You can see that sometimes restricting the domain is what allows its inverse to be a function. If f of x represents a function, then the notation, look at this, f negative 1 of x. We're going to read that as f inverse. We're going to use a little negative 1 symbol. We would do the same thing for g of negative 1. So we call that g inverse. Don't get that little inverse confused with thinking that this is going to be 1 over f of x. That's not equivalent. That's not what we're saying. It's not negative exponents. It's just representing that it's going to be an inverse. All right, so now we're going to talk about finding the equation of the inverse. So what we're going to do, if necessary, we're going to replace function notation with a y. Then we're going to switch the variables x and y. We're going to put the y value inside the equation. We're going to put the x value on the outside. Then we're going to solve for the new y. So it's pretty straightforward. But it is math. So we're going to take our equation. It's already with y. So we're just going to switch the x and the y. Multiply the 4 because we're solving for y now. Then we're going to divide by the 7. So this becomes 17x plus 4/7. That is going to be the new y value. We're going to call it f inverse of x. Right up here, right using inverse notation, if y was the original, use f inverse of x. So that's why we used f inverse of x. That's our inverse function. The original graph would have been something down at -4, up 7 over 1, up 7 over 1. So it's going to look something like that. So when you reflect it over the line y equals x, what used to be negative x's is now going to become, or negative y's actually, is now going to become negative x's. Wherever it crosses your line of reflection, it's still going to cross there. So this is f inverse of x. This is f of x. This new equation crosses above the x-axis, so that's why it's positive 4/7. And it's very flat. It's up 1 over 7, up 1 over 7. So that makes some sense. So we first have to turn f of x into a y. Then we switch the x and the y. And we solve for the y. We're going to divide by -5 to both of the terms. That's going to give us -1/5 x plus 2/5. And that's going to be f inverse of x. Very similarly, we have 2/3 x minus 5. We switch our x and the y. So we add the 5 across. So this is x plus 5 equals 2/3 y. We would multiply by 3. And when we multiply by 3 on this side, we need to be sure to distribute that in. So that's going to become 3x plus 15. That's going to equal 2y. Then we would divide by 2 to each term. So that's going to be 3/2 x plus 15/2. And we could call that f inverse of X. Now look at this last one, or this next one, very carefully. This is different, so pay attention to this. We're going to first change function notation over to y. Then we're going to switch the x and the y. Notice that I did not take the negative with it. I'm only switching the variable. I'm not switching the coefficient that's in front of the variable. So we're going to subtract the 7 over to get x minus 7 equals negative y. Then we're going to divide by the negative 1 to each term. That gives us negative x plus 7 equals y. So we're going to say that that equals g inverse of x. Do you notice anything funny about this inverse? It's the same as what we started with. Because this equation is perpendicular. There's our y equals x. Up here at 7, it would be perpendicular to that. It's got to cross at 7, and it's going to come down with a negative slope, which is perpendicular to y equals x. When you reflect it, it's just going to reflect right on top of itself. Y equals negative 3/4 x plus 9. Switch the x and the y. Subtract the 9. Then we're going to multiply by the denominator. That means we have to distribute it through. And we divide by our 3 to every term. So that gives us negative 4 over 3x plus 12. And that's going to be h inverse of x. So we're going to look at a story problem now. A small company produces greeting cards. The cost in dollars of producing N greeting cards per month can be modeled by this equation. The cost equals $360 plus 60 cents for every card. Now, here's the important part. This is the part you don't want to miss. Do not switch the variables when finding inverse models, because the letters stand for more things. Okay, we can't just all of a sudden say that the cost and the number of cards is switched. So we're going to start with C equals 360 plus 0.60n. We'll minus 360 to the other side. that C minus 360 equals 0.60, but instead of saying 0.60, I'm going to say 6/10. You can even call that 3/5 if you want. So we're going to multiply through by our 10. That's going to cross the denominator out. Distribute gives you 10C minus 3,600. And then we divide by 6 to each term. That gives us 5/3 C minus 6 goes into 36 6 times with 2 zeros. That's the number of greeting cards. So the number of greeting cards is going to be 5/3 the total cost minus $600. So if you're trying to find the total greeting cards of a certain price of cards, how many did you make if you have $1,000? How many did you make if you have $2,000? Well, in this case, we're going to have $615. Use the inverse function to find the number of greeting cards produced in a month in which the company's total cost is $615. So our total cost is going to be $615. So we can reduce the denominator with what we're multiplying. So that is 5 times 205. That's going to become 1025. $1,000 minus 600 is 400. So this is going to become 425 cards. So you're going to make 425 cards if you have a total cost of $1,650 or $650. Sorry, $650.